In this video, I'm going to discuss on the enzymatic browning. So, most of you have know this, where enzymatic browning usually occurs in many fruits and vegetables. So, when the tissue is cut or peeled, it rapidly darkens on exposure to air as a result of conversion of phenolic compound to brown melanoidins. So it involves a copper cofactor, and this reaction or this enzymatic browning is usually active between the pH of 5 to 7. Okay, if you look at the picture here, this is the fresh apple. So when you cut it, so they will have some browning here. The one that is shown by this arrow. So this one will have some enzymatic browning. And then when you have a banana, you peel the skin, and then after some time, it will turn into brown at some parts of the fruits. Okay, when you cut a potato also, you will notice that there are some browning after you leave it exposed to air for some time. And then this browning involve what we call as phenolic substrate. So phenolic compounds are widely distributed in the plant kingdom and are considered to be secondary metabolites. So structurally, they contain an aromatic ring bearing one or more hydroxyl groups. Okay, that's why when we talk about antioxidant in food, normally fruit and vegetable has lots of antioxidant compound because they have lots of phenolic compound. And you see, these are some of the phenolic compounds that can be found in vegetable and fruits. For example, this gallic acid, you see so many OH group here. And then chlorogenic acid also has OH group. And then anthocyanin is one of the flavonoid. Yeah, you can found and it responsible for the color for the fruits or vegetable. Yeah, see there are so many OH group here. So this is what we call as phenolic substrate or antioxidant compounds. Yeah, that can be found in fruits and vegetables. Okay, so this enzymatic browning is catalyzed by this enzyme, polyphenol oxidase, which catalyze the oxidation of phenols to orthoquinones, which are highly reactive compounds. Yeah? Orthoquinone then undergoes spontaneous polymerization to produce high molecular weight compound or brown pigment or melanin. Okay, so what happened? You have a phenol. So in the presence of PPO, polyphenol oxidase, so it will give you orthoquinones. So this orthoquinone polymerize, so meaning you have lots and lots unit of this orthoquinone. So this lots of unit will eventually converted into high molecular weight compound, which is the melanin. Yeah, melanin. So this melanin in turn react with amino acid and protein, leading to enhancement of the brown color produced. Okay, so when this melanin found amino acid or protein, so they will give it will enhance the brown color that was produced. Okay, so in enzymatic browning, quinone formation is both dependent on the enzyme and oxygen. So if the enzyme is high, the concentration of enzyme is high, but it is low oxygen, so the quinone formation is not that much, compared to if you have both enzyme and oxygen at high level. So once the reaction started, the subsequent reaction occurs spontaneously and no longer depend on the oxygen or enzyme. So enzymatic browning, the enzyme only involved at the first step. For example, phenol, phenol to orthoquinone. Okay, this is the next step lah. Okay, so the first step here, which is highly depend on the oxygen and enzyme. So if you do not have enzyme here, so phenol won't be converted to orthoquinone. Okay, this is an illustration of the reaction on the enzymatic browning. So you have this phenol compounds. Doesn't matter what is the substituent group, as long as it has a benzene and OH, it is a phenol. So this is a monophenol compound because you only have one unit of phenol. And then in the presence of polyphenol oxidase plus oxygen, it will give you a diphenol. So this is the diphenol. So diphenol, when you introduce another enzyme and oxygen, it will give you a quinone, which is the colored compound. So this quinone, it polymerizes, and then when it react with amino acid or protein, it will give you complex brown polymers. Okay, how do we control the enzymatic browning? So enzymatic browning can be inhibited by targeting the enzyme, targeting the substrate, or targeting the product. Because you know every reaction has starting material, and then you have this condition or reagent, and you have the product. So these are three things that you can control. First one, the first alternative is we inhibit the targeted toward the enzyme, and the second one, inhibition is targeted towards the substrate. Okay, enzyme first and then substrate, and the third one, inhibition targeted towards the product. Okay. So the first one, the first alternative is inhibition targeted towards the enzyme. Okay, we can use inhibitors which act directly on the polyphenol oxidase, the PPO. So we can use chelators like azide, cyanide, carbon monoxide, halide ion, and tropolone. So these are some of the chelators that are well documented for the inhibition of polyphenol oxidase, meaning that these chelators can form complex with this polyphenol oxidase so that it won't react with your material lah. Okay, another type of chelators also some phosphate, EDTA, and also organic acids. Okay, this is still number one, inhibition targeted towards the enzyme. So another way is we can deactivate the PPO using heat treatment, such as steam blanching. So effectively applied for the control of browning in fruits and vegetables to be canned or frozen. But heat treatments are not, however, practically applicable in the storage of fresh produce. Okay, for example, let's say you want to can some pear, you want to make it into, you want to can it. Okay, so what you can do, the pear is being steam blanched so that you can deactivate the polyphenol oxidase, so that in the can it will not goes brown. Okay, that is how you can improve the aesthetic of the fruits. Yeah, who wants to eat a canned fruits that already brown? Okay, so that's how they do it. They use heat treatments, steam blanching, to deactivate the PPO on pear, for example. Okay, so the second approach is inhibition targeted towards the substrate. So um, elimination of oxygen from the cut surface of fruits or vegetable greatly retard the browning reaction. So exclusion of oxygen is possible by immersion in water, syrup, or by vacuum treatment. Okay, so vacuum packaging of pre-peeled potato to exclude oxygen was observed to extend their shelf life. However, vacuum packaged product rapidly undergo browning upon exposure to air. So once it being released from the vacuum, it will rapidly undergo browning once it is exposed to air. Okay, this one you can also observe in like longan in syrup or pineapple in syrup. Okay, pear in syrup. Okay, this is how they eliminate the oxygen from the cut surface of fruits. Okay, by using this possible treatment. Yeah. Okay, still number two, another way to inhibit inhibition targeted towards the substrate. So we can also use vacuum packaging. However, vacuum packaging has some safety concern because the anaerobic condition inside the vacuum packaging potentially capable of supporting the growth of Clostridium botulinum, which is a bacteria that can produce a toxin. Okay, so we can also add some compound, for example, a sulfated polysaccharide to have inhibitory effect on the browning. So this sulfated polysaccharide, they can form a possible complexation through chelation of the copper group of the polyphenol oxidase. Okay, so because sulfate, you know what you have learned in inorganic chemistry. So S has lone pair, so it can react with the polyphenol oxidase because of the copper group. It can form a complexation with the copper group, where this sulfur can donate electron to the copper ion. Yeah. Okay. So still number two, inhibition targeted toward the substrate. So you can also add a specific adsorbent which can undergo complexation with the phenolic substrate, and it can be applied in the physical elimination of a phenolic compound from the food system. And also you can use cyclodextrin for the removal of phenolic compounds from raw fruit and vegetable juice. And this one has been patented in the United States. And cyclodextrin are thought to inhibit PPO activity through the formation of inclusion complexes with polyphenols. Cyclodextrin is like a supramolecule um, that can protect the polyphenol. Okay, you have polyphenol. It's like this is your polyphenol. This is the macromolecule, supramolecule, the cyclodextrin. So it can form like a barrier here. So your polyphenol will not react with the PPO. Okay, so it can protect it can protect the polyphenol here from reacting with the PPO and avoid browning. Okay, in the substrate, you can also do some enzymatic modification of phenolic substrate. So it may serve to inhibit PPO activity. Yeah? And then you can add enzyme or methyl transferase. For example, it converts the phenolic to the corresponding methoxy derivative, which is not a substrate of polyphenol oxidase. Ya. Contohnya, if you have dihydroxyphenolic, example, this is like phenol compound, dihydroxy. Okay, so you can convert this hydroxy group to CH3 or OCH3, methoxy OCH3, OCH3. So once it is being substituted, it no longer can react with the PPO. So this involves the use of this enzyme, methyl transferase, meaning this H is substituted by the CH3. And similarly, you can also add some this enzyme. Okay, so it will modify your phenol compound so that it won't react with the PPO. And these enzyme modification techniques are not, however, feasible in commercial use because the high cost of this enzyme. So enzyme is very expensive, so sometimes it is not feasible to use in commercial use because it will increase the price of your product. Okay. Okay. Still number 2. Inhibition targeted towards the substrate. So orthoquinone, which is the product of the diphenyl oxidation, is capable of reacting with each other, so they result in the formation of dimer. And this dimer has orthodiphenolic structure, and in order to inhibit the conversion of O-quinone to the O-diphenolic, so you can use ascorbic acid, thiol compound, or sulfide. So this type of compound can inhibit dimer formation. Okay, dimer formation from orthoquinones to orthodiphenolic, and or through the formation of colorless addition products. Okay, so in the next video, I will continue on this. I will continue on the next inhibition strategy. So thank you for listening.